Так, добрый день. Начинаем лекцию. So in the last class we considered Hamming code. I will recall now what parameters Hamming codes have. So m is an arbitrary integer, and for every m there is a Hamming code with parameters 2 to the m minus 1. This is the block length. The dimension is m bits less, 2 to the m minus 1 minus m. And the minimum distance is 3. And this is a binary code. Using standard procedure, we can transform this code by increasing the minimum distance by 1 and also the block length by 1. This was one of the problems for you to solve at home, namely problem 2. And we will obtain the code with parameters 2 to the m. The dimension doesn't change. And the minimum distance becomes 4. These are also called Hamming codes. And the parity check for those codes looks as follows. The first row consists of all ones. This means that in every code word, the sum of all symbols modulo 2 must be equal to 0. So all code words have even number of ones. And the remaining part of the matrix is just the parity check matrix of the normal Hamming codes. In other words, the first column consists of only zeros, and all the remaining columns are all non-zero vectors of height m. So this is m. So the total height is m plus 1. So we have m plus 1 equations, and this is the parity check matrix. So we list all the columns of height m. And so we have m plus 1 equations. We have 2 to the m variables. So the block length is 2 to the m. The dimension is 2 to the m minus the number of equations. And because of this additional constraint, the minimum distance becomes 4. Indeed, if the code words for this code are obtained from the code words for the initial code by adding 1 bit, which equals to the sum of all the remaining bits modulo 2. So if 2 code words from the previous code were at distance exactly 3, then the number of ones in them was different, and so the first bit in those 2 code words will be different, and so they will have an additional position where their bits differ, and so instead of 3, we obtain 4 positions where the code words differ. And if the distance was already at least 4, then adding a new bit doesn't decrease it anyway. Okay, so now we will give up Hamming codes and consider a new family of codes, which is called Reed-Solomon code. Reed-Solomon codes. These are the most famous and widely used codes in computer science. To introduce them, first I will switch to a new blackboard. Is it shared or not? Let me see. Oh no, it's not shared yet. So I have copied the link to the new blackboard in the chat. And do you see the new? Can you see now the new blackboard?
Yes, we can.
Okay, good. So I will use now that one. And I will start with the so-called Singleton Bound, because the Reed-Solomon codes are closely related to the Singleton Bound. So what is Singleton Bound? I recall the graph of the Gilbert bound. Assume that the alphabet is very large, Q is large. Then it looks like that. It starts from 1 and it reaches the x-axis in a point which is very close to 1 again. More precisely, this point is 1 minus 1 over q. But if q is large, this is almost 1. So this is the d over n axis. This is the k over n axis. So, and the Gilbert bound indicates the area where there is a code. So this is the yes area. For these values of parameters, we know the code. And the second one, the Hamming bound, is obtained from the Gilbert bound when we stretch its graph 2 times along the d over n axis. So it becomes something like that. So the Gilbert bound for a very large Q is close to the line and also the Hamming bound. And this is because the Shannon function has the following formula. Its value in P is equal to something, more precisely to log Q 1 over P times P plus y minus P log Q of 1 over 1 minus P. But when Q is large, this is not important. And the most important is the second term, which is log Q over Q minus 1, base Q minus 1 times P. And if Q is very large, then this is very close to 1, and this is close to 0. So this is approximately equal to just P when Q is large. So we assume that Q is large. And that means that this line, this bound is very close to the straight line from 1 to this one. And this one is also close, the Hamming bound is also close to the straight line. But the Hamming bound is now very big because it's very high. So it indicates the no area. And this unknown area in that case can be actually diminished. So when alphabet is large, then I'm sorry, there is a universal bound, doesn't depend on the alphabet, which is called Singleton Bound. And that bound is almost equal to the Gilbert bound if the alphabet is very large. So the Singleton bound looks like that theorem. It provides, again, a sufficient, a necessary condition for existence of n k q d, sorry, over q letter alphabet code. And it's very simple. If a code with parameters n, q, d exists, then q, k plus d is at most n plus 1. In other words, k over n plus d over n is at most 1 plus 1 over n. And that means that actually this question mark unknown area shrinks to almost nothing. So because this Singleton bound increases the no area almost to the whole this region. So now we know that there is no code for which the parameters lie above this straight line. And here is the proof of this fact. Assume that NKD code exists. Then we can transform it to n minus t, k minus t, k minus t, d code over the same alphabet. For any t, which is at most k, otherwise this is negative, using the following simple observation. We will use the so-called pigeonhole principle. In Russian, it's called принцип кроликов или принцип Dirichlet. So in English, they call it pigeonhole principle because, and it states that if we have k pigeons and k minus 1 holes, then there is a hole, and every pigeon sits in a hole, then there is at least one hole in which there are two pigeons. Or more generally, if there are n pigeons and k holes, then there is a hole in which there are at least n over k pigeons. And here we can, around n over k, consider to the largest integer, to the smallest integer, which is larger than n over k. That means we can take the ceiling, not the floor. And in our case, the pigeons will be code words, and the holes will be their t-length prefixes. So we consider all the code words, and we consider the first t bits in all code words, and the total number of prefixes of length q to the t is q to the t, and hence there is some prefix for which at least q to the k minus t code words have that prefix. So by the pigeonhole principle. So there is a string, call it say y, of length t, such that the number of x's code words which are in our code and that have that prefix is larger than q, the number of code words q to the k minus divided by the number of prefixes q to the t. That means q to the k minus t. So then we take all those q to the k minus t code words, erase the prefix, and so we obtain code words of length n minus t because we have trimmed the first t bits. And we keep the minimal distance because all those code words had d positions in which they were different. However, they equal in the first t bits, t positions, and hence all the differences fall into the last n minus t bits. And so we keep the minimal distance. So, and this transformation works for any t. But we will use a specific t. We will use the largest t for which k minus t is still positive, because we need that in the resulting code there are at least two different code words. And so we take we let t be equal to k minus 1, and so we obtain from the initial n k d code the code with parameters n minus k plus 1, 1, and d. And now we see that the length, so there are at least two code words, and they differ in d positions, but the total number of positions in our word, in the code words, is n minus k plus 1. So we can easily conclude from that n minus k plus 1 is at least d. So the length, block length should be at least the minimal distance, which is obvious. And in other words, n plus 1 must be larger than or equal to k plus d. And this is the Singleton bound. So the Singleton bound, I mean, that bound doesn't depend on the alphabet. This is true for every alphabet, but for a very large alphabet, this is tight. So it almost matches the Gilbert bound. And so if alphabet is very large, then the picture becomes clear. We know for which values of parameters k over n, d over n there is a quote, and for which there is not. But in this phrase, something is very imprecise. That means I have said that for a very large alphabet, but what means very large? And actually this question may be answered very simply. Very large means larger than n, the block length, because we will now present a family of codes which match, which attain Singleton bound if the cardinality of our alphabet Q is n or larger. And these are called Reed-Solomon codes. So Reed-Solomon codes will lie on the Singleton curve. That means that they are perfect. Moreover, for every point on the Singleton bound, there is a Reed-Solomon code for that parameters. The only minor point of Reed-Solomon codes is that the alphabet should be large. They have the alphabet which is larger than or equal to the block length. And the other minor point is that the cardinality of alphabet should be a power of a prime, because Reed-Solomon codes are also linear codes. So they need a field structure on the alphabet. So assume that P is a power of a prime. So we will obtain then, we'll consider field of Q elements denoted by FQ. And the parameters of Reed-Solomon codes will be M, K, and the distance will be exactly as required by the Singleton bounds. That means that D will be equal to N plus 1 minus K. And the alphabet will be Q, and N must be less than or equal to Q. This is very important. So for every N, K, and Q satisfying these constraints, that is that Q is a power of prime and Q is larger than N, there is a code with those parameters, with these parameters, called Reed-Solomon code. And now I will define what is this code. So the messages will be viewed as polynomials of degree k minus 1. So the message say m0, m1, mk minus 1. So this is the sequence of letters, that means the sequence of elements of the field, will be viewed as the polynomial p of x, which is m0 plus m1x plus mk minus 1 x to the k minus 1. So this is degree k minus 1 polynomial. And the code of that message, the code which encodes such message is the value of that polynomial in some specific pre-chosen elements of our field. So we choose some elements, pairwise distinct elements in our field. And to this end, we need that Q is at least n, otherwise there are no pairwise distinct elements in the field. And it's not important which elements to choose and how to arrange them. So fix n different elements, fix their order, any order, And then we obtain a code, a Reed-Solomon code. And again, the message is considered as a degree k minus 1 polynomial, and the code words corresponding to that message is the value of that polynomial in those fixed endpoints. Otherwise, we will call also the table of that polynomial, table of values. And now you see that the block length is indeed n, the message length is indeed k, and simple algebraic theorem, the well-known algebraic theorem implies that the minimal distance is at least n plus 1 minus k. So let's call it theorem. The minimum distance is at least n plus 1 minus k. And here is the proof. So what does it mean that the minimal distance is at least that much? That means that if we have two different polynomials, P is different from Q, then they differ in that many points or more. In other words, they coincide in at most k minus 1 points. So we need to prove that there are at most k minus 1 points xi such that P of xi is equal to Q of xi. But what does it mean that P of xi equals to Q to xi? The reformulation of this is that the difference of those polynomials, P minus Q, has xi as a root. So P minus Q is non-zero polynomial of degree at most k minus 1, because both polynomials P and Q have degree at most k minus 1. And we know that the number of roots of a non-zero polynomial is at most its degree. It's an algebraic fact. And degree is k minus 1. So the number of xi where P and Q coincide can't be larger than k minus 1. So this completes the proof. So let's consider an example of Reed-Solomon code so that you get accustomed, you get used to these codes. So this simplest example, I think, is when the alphabet consists of 3 letters, 0, 1, 2. The block length is also 3. The dimension is 2, and the distance is also 2. And actually, this code solves one of the problem for the code for today's homework. So you will see now that most of you have just found that Reed-Solomon code without knowing it in advance. So the messages will be here non-zero, polynomials of degree 2 minus 1, that is 1. And there are 9 such polynomials, constants 1, 0, 1, 2. Now the polynomial x plus 1, and x plus 2. And the polynomials 2x plus 1, 2x plus 2. So these are 9 possible messages. Now, the code words consist of the tables of all the polynomials in some 3 points, but in this case, we need to evaluate our polynomials in all the points of the field, because Q is exactly equal to L. So we need to compute the the values of this polynomial in these 3 points. So the constant constants produce the code words consisting of the same letters 0, 0, 0, 1, 1, 1, and 2, 2, 2. Now the polynomial x produces the code word 0, 1, 2. This x plus 1 produces the code word which is obtained from this by shifting by 1, that is 1, 2, 0. Now we again shift that code word by 1, we obtain 2, 0, 1. Now 2 times x produces the code word 0, 2, 1. And again we shift it by 1, 1, 0, 2. And the last one is again obtained by shifting this by 1. We obtain 2, 1, 0. So we obtain 9 code words, and we see that all they are pairwise different, and moreover, the number of different positions is 2 or more. So this is not a code word, these are code words. So these 3 are pairwise different, and the difference is 3. I mean, they differ in all 3 letters, and the remaining code words differ from those in 2 positions. And some of these also differ from each other in 3 positions. So the minimum distance is here equal to 2. Of course, this set of code words may be found just by a small search, and we do not need to understand that this is the Reed-Solomon code to find it. But for larger alphabets, it's not very easy to find such code words. Now we will discuss how to encode and decode Reed-Solomon codes, so encoding and decoding. For encoding, we just need to understand how to add and multiply elements in the field of Q. This actually is out of scope of our lectures. There is an efficient algorithm to find the representation of FQ so that we can easily to find the sum and the product of any 2 numbers, and also divide and subtract. And we will assume that somebody has already provided to us such a representation. Then encoding is just evaluation of the given polynomial in given points, and this can be done very easily. Actually, there is a so-called Gorner scheme to find the value of polynomial in a given point, and this is done as follows. So encoding may be done in a linear time, assuming that the field operation costs 1 unit time. So we take the last letter of our message, mk-1, add x k minus 1, I guess, multiply by x kind of minus 1, add mk minus 2, multiply by x k minus, sorry, not, if you want to find the value in the point xi, we should use xi everywhere, not xk minus 1. Xi here, xi here. And so on. So using this Gardner scheme, we can compute the value of the given polynomial in linear time in 1 point, and we need to compute it in n points. So we will use approximately nk field operations for that. And decoding is much more expensive, of course, because when we speak about decoding, we usually mean decoding which corrects error. But let's start first with decoding where we know that there are no errors at all. So decoding without correcting means that we have the value of our polynomial in some n points, and actually to find the polynomial we need only its value in k different points where k minus 1 is its degree. And correcting means that we want to find from the values of that polynomial in k points its coefficients. So from that, we want to find coefficients of P. And it is well known how it can be done. There are two known ways. The first one is when we use Lagrange interpolation, Lagrange polynomials. So the polynomial P can be expressed as this linear combination of some polynomials called Lagrange polynomials, where coefficients are the values we are given. And that polynomial has the following feature, that Li evaluates to 1 in the point xi, and Li evaluates to 0 and all the remaining points. And such polynomials, such polynomial Li has an explicit formula. Li, let me write the formula. Li of x is equal to the product of x minus xj over where j ranges overall indices different from I, over the product of xi minus xj, where again j ranges over or indices different from y. And you see that if we substitute here x with xi, everything cancels and we obtain just 1. And if we plug xj for x in this expression, then the numerator becomes 0 and the value becomes 0. So we have verified that Li has indeed that feature. We see that Li has degree k minus 1 because here is the product of k minus 1 linear expressions, linear in x. And so this sum meets all the requirement. It is the polynomial of k minus 1 of degree k minus 1. It evaluates to the given values in all k points. And this is our message. So this is the first method. And the second method to recover the message from its code word is by solving the system of linear equations. So solve the system. And the system looks like that. For each xi, we just write the formal expression m0 plus m1xi plus blah 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 mk minus 1 times xi to k minus 1 is equal to p of xi. So we have to write this equation for I from 1 to k. So we have k equations. The variables here is the unknown symbols of the message. M0, M1, Mk minus 1 are our variables. Xi's are some specific numbers. So this is a linear combination in mj's. And p of xi is also a specific number given to us. It's the value of our polynomial we are given. And so we have a system of k linear equations in k variables. And it has, as well-known, single solution because the matrix of this system is a well-known van der Waals matrix. Its determinant is non-zero, and hence such a system has a simple, a unique solution. And we can solve this system just using the method of Gaussian elimination or any other efficient algorithm to solve a system of linear equations. So this is the second method to decode Reed-Solomon code when we have no errors. Так, давайте сделаем перерыв на 5 минут, значит, продолжим час 20. Okay, so we have discussed how to decode read Solomon codes when we have no errors, and we will proceed to the case when we have some errors. So let's start the new slide. So decoding from errors. So what do we know? So we have some unknown polynomials, polynomial P. We have evaluated it in some n points. But then some values were corrupted. And let's call the corrupted values tilde P of x1, tilde P of xn. And we have a promise that here at most E errors, at most E values are bad, are incorrect. Where E is the maximal number of errors the code can correct, which means that E is D minus 1 over 2. That means that E is N minus K over 2, and we take the ceiling of this. So at most this much errors are incorrect. Let's assume that exactly E, let's assume that exactly E values are incorrect, and write here an inequality. So E is at most that. So okay. Now our goal is to recover the coefficients of our polynomial. How do we do that? We will do it in 2 steps. On the first step, we will solve a system of linear equations, and now I will explain which one. So we will use some generalization of the second method to recover the coefficients. So we will solve a system of linear equations. So to understand what are our equations, let's start with the following observation. Let's consider the function tilde P. This is not a polynomial because we have at most, we might have incorrect values here. And let's multiply this function by a polynomial which is 0 in all the places where there is a rector, an error. So Q is the product of x minus xi over all i's such that x P of xi differs from tilde P. of xi. So to say, Q is annihilator of errors. It annihilates in all in all points where you have an error. So then this polynomial is equal to P of x in all the points This is equal to P of x, Q of x in all points. So this for all i's, this is the same as P of xi times Q of xi for all I starting from 1 to n. Again, if xi is an error, then both the left-hand side and the right-hand side is 0. If xi is not an error, then the left-hand side is the same as the right-hand side because tilde p and p take the same values. So, and now observe that this is a polynomial of degree at most so Q, P has degree k minus 1. And Q has degree e. So the degree of this polynomial is at most k plus e minus 1. And this guy, Q, has degree e. So now we have proved actually the form lemma, call it lemma 1. There exists a non-zero polynomial of degree e and a polynomial maybe zero. I'd call it Q, the polynomial Q of degree e, and the polynomial R, call it this one, call it R of degree at most k plus e minus 1, such that we have the following inequality: tilde p of q of xi times q of xi is the same as r of xi for all i's. From 1 to n. Of course, there might be polynomials q and r satisfying this lemma, which are different of those we had. So q must not be an annihilator of errors, and r can be different from p times q. But in the sequel, we will need some q and r satisfying these properties. And on the step 1, we will find a polynomial, we will find some q and r satisfying lemma 1 just by solving a system of linear equations. As we have noted, if we understand the coefficients of q and r as our variables, as our unknowns, then both r of xi is a linear expression, a linear combination of our variables for each particular I. And also Q of xi is a linear combination of our variables. Tilde P of xi is some specific number given to us. Hence, every such equality is actually an equation, a linear equation in our variables. We will write this system and solve it. There is only one problem considering this system. We do not know the number of errors in advance. And hence, we will assume, again, that the number of values which are incorrect is at most e, where e equals exactly to this value. And in our lemma, we will still require for a polynomial of degree exactly e. And to prove the lemma for that e, we just can take our annihilator and then multiply it. If the number of actual errors is strictly less than e, we can multiply q by any polynomial so that to make its degree as required. Or we can just say that degree of q is at most e, then it's okay. So we will have then e plus 1 variables for q, k plus e variables for r, solve this system and find such q and r. So step 1 of our algorithm will be finding q and r as in lemma 1. Now we will proceed to the second step. For the second step, we will need the second lemma, which state that actually if q and r satisfy lemma 1, then q is divisible by r is divisible by q, and moreover, the quotient is equal to p. Then p of x is equal to q of x times r of x is equal to q of x times p of x. How to prove it? First, we will see that this equality, here we mean an equality as equality of polynomials. But let's first prove that the polynomial r has the same value as the product of polynomials q and p in all our endpoints. So first, let us show that r of xi actually this is not true, not in all endpoints, in n minus I points. Let us show that r of xi is equal to q of xi times p of xi for all but ei's. And this equality holds in all the points for which p is the same as tilde p. Because if p of xi is equal to tilde p of xi, then certainly p of xi times q of xi is the same as tilde p of xi times q of xi, and by lemma 1, this is equal to r of xi, because tilde p of xi times q of xi is equal to r of xi for all i's. And so we obtain that this inequality holds for all points except some, maybe some e points. So that means that this inequality holds in at least n minus I points. And if two polynomials have the same values in some points where the number of points is larger than the degree of polynomials, then those polynomials are actually equal as polynomials. They have the same coefficients. So let's count the degrees. So the degree of R is at most, let's see, what is by lemma 1, the degree of R is k plus e minus 1. And the degree of QP is also that much, because Q has degree E or less, and P has degree K minus 1. So both left-hand side and right-hand side have degree at most K plus E minus 1. And we need now to verify only one simple inequality. We need that this is less than the number of points strictly less, sorry, we need that this is strictly less than the number of points where they coincide, which is n minus I. So that means that we need that 2e is strictly less than k n minus k plus 1. Or in other words, we need that 2e is at most n minus k. But this is given to us as our assumption, because our e is actually n minus k over 2, the floor of that. That means that 2e is anyway at most n minus k. So we are given that as our assumption, actually. This is our assumption, because we have chosen e to be so that this inequality holds. And this concludes the second step, the proof of the lemma. And so we have two polynomials, q and r, and we know that r is equal to q times p. Then it's easy to find p just dividing r by q. So on the second step, we divide r by q. And so to perform this step, we need that q is non-zero polynomial. Using the known algorithm, it's called in English long division algorithm. In Russian, it's called деление уголком. So we write p r here, we write q here, and we obtain p as a quotient. So I assume everybody knows long division algorithm, so there is no need to recall it. So the long division algorithm works again in linear time, assuming that the operations in our field doesn't cost anything, so they are performed in unit time. And so this concludes our algorithm. We have designed a very efficient algorithm to decode the Reed-Solomon code from as much errors it decodes, it corrects. So let me recap everything. So Reed-Solomon codes lie on the Singleton Bound, this one. And for every point on that bound, there is a special Reed-Solomon code. So there are many Reed-Solomon codes. For every point on that line, there is a special code. Because they lie on the curve which bounds the area where there is no code, they are perfect, so they can be improved. And they are efficient in the sense that both encoding and decoding from errors algorithms are very fast. So everything is good for Reed-Solomon codes, except that they need a large alphabet. So they can be used only when the number of letters in our alphabet is larger than the block length. And also there is another restriction that Q is a power of a prime, but this is not very important. This one is the main constraint, which bounds the usage of Reed-Solomon codes. And we will, in the future classes, we will discuss how to overcome this problem, how one can decrease the number of letters in Reed-Solomon codes. Of course, we will decrease it using, we will pay for that. And the payment will be that we decrease both relative distance and rate. So we will discuss how using that transformation we will obtain the reasonable codes. Так, давайте сегодня я закончу лекцию, потому что тест сегодня довольно сложный, ну, там, требующий времени скорее. Значит, поэтому я вам дам тест не как обычно на 10 минут, а вдвое дольше, на 20 минут. Скопирую его на, значит, чат. Так. Так, значит, сейчас у нас, ну прям без 15 сейчас ровно, значит, 14:05, конец. Ну вот смотрите.
По этой ссылке написано, что нет доступа.
Нет доступа, извиняюсь. Сейчас доступ будет. Сейчас. Мгм, так. Сейчас я на всякий случай скопирую, может, ссылка изменилась после этого. Ой. Так, сейчас изменилось. Да, изменилось. Вот, вот это вот, использовать другую ссылку. Так, ну все равно, значит, 14:05 конец. Сейчас, что-то я не помню, не понял. Вы все корректируете и вы меняете. Это вот совсем нехорошо. Или это мне кажется?
Да, вы дали нам
Да.
редактировать саму форму, а не
Ой-ой-ой, нет.
отвечать на нее.
Извиняюсь, это совсем не этого не хотел. Значит, сейчас опять придется что-то изменять. Так. Да-да-да, can edit, это совсем плохо. Anyone with the link? Сейчас тут не эдитор. Уже это сделать.
Так что, уже работает все или как?
Сейчас, нет, мне пока не удалось сделать, чтобы вы могли отвечать, но не могли редактировать. А, вот кажется, сейчас удастся. Вот. Во-во-во-во. Anyone with the link? Во-во-во. А, нет, editor. Сейчас, подождите еще раз. Так, ну давайте посмотрим еще раз. Я попробую. Сейчас попробуйте. Можете вы отвечать? Вот эту ссылку откройте.
Да, нормальная Google форма.
Угу. Ну хорошо, ладно. Тогда, если хотите, будет 20 минут, значит до 10, 14 10. Ну, наверное, большинству и 15 хватит. Только, правда, первое, это самое, кто-то заменил на question. Самое первое, где фамилию нужно написать. Сейчас я исправлю это. Так, вот я исправил. Первый там фамилию, номер группы надо написать. Так, последняя минута пошла. Так, ну, собственно, все сдали, как я понял. Уже смотрю. Сейчас, даже лишние. Те, кто не присутствовал, некоторые еще тоже сдают. Так, ну все, я закрываю. Так, ну ладно, все тогда, до свидания, всего хорошего.
До свидания.